A house sparrow lands on a branch. At first glance, it seems far removed from the giant dinosaurs that once dominated the land. Its body is small, its jaws have no teeth, its fingers are hidden inside wings. Yet this animal is a dinosaur. It belongs to the only theropod dinosaur radiation still alive today. Beneath its feathers, each wing contains a reduced and fused dinosaur hand. Its chest carries a wishbone inherited from non-avian theropods. Air sacs extend into parts of its skeleton. Even its two-legged stance belongs to a body plan established deep inside theropod evolution. The sparrow did not appear through one sudden transformation. Its anatomy was assembled across many branches and over immense spans of time. Feathers appeared before flight, small bodies appeared before powerful wings. Wrist, shoulder, chest, tail, and balance changed at different rates. So the real mystery is not when one dinosaur stopped being a dinosaur. It is this. What had to become true before a dinosaur body could fly? The answer cannot be arranged as a line of species. Tyrannosaurus did not become Velociraptor. Velociraptor did not become Archaeopteryx. Archaeopteryx was not simply the next step toward a sparrow. They occupied different branches of the theropod family tree. Within coelurosaurian theropods, several branches accumulated features that also appear in birds. Some remained completely terrestrial. Several approach-tested aerodynamic thresholds. Relatively few clearly crossed all the thresholds proposed for powered flight. Within avialia, the lineage leading to crown birds survived beside many other branches that later disappeared. This changes how fossils should be read. A fossil does not need to be a direct ancestor to preserve decisive evidence. One animal can show that feathered skin existed before flight. Another can preserve a specialized wrist. A different branch can reveal an aerial design that left no descendants. The evidence is distributed across the tree. The first requirement was already present, while these animals still lived entirely on the ground. Sinosauropteryx was a small, ground-running theropod with short forelimbs and no flight-capable wing. Fossils preserve simple filamentous structures around its body and long tail. These coverings lacked the organized veins that allow modern flight feathers to act as strong aerodynamic surfaces. They still changed the animal. A filamentous coat could help manage body heat. It could carry visible patterns used in display or communication. Other functions may also have mattered. The first evolutionary origin of feathers and their earliest function remain open scientific questions. Sinosauropteryx also preserves pigment evidence. Melanosomes from its tail support a banded pattern containing darker reddish-brown or chestnut areas. The fossil does not reveal a completely certain whole body palette, but it does show that the tail carried a deliberate visual pattern. Later non-avian dinosaurs possessed much more complex feathers. The forearm of Velociraptor preserves a row of attachment bumps interpreted as quill knobs. In living birds, similar structures anchor large feathers to the bone. Velociraptor could not perform powered flight. Its quill knobs prove something different. Large, structurally complex forearm feathers existed in a non-avian dinosaur. Feathers therefore had a long evolutionary history before some branches turned them into an airfoil. A feathered surface now existed. One major problem remained. The body carrying it was still built mainly for life on the ground. Along the lineage approaching birds, theropods underwent a sustained long-term reduction in body size. This was a branching trend, not a perfect staircase. Some small branches never flew. Some later lineages became large again. Still, miniaturization changed the physical demands of aerial movement. Less total weight had to be supported, while feathered forelimbs became proportionally more useful for controlling the body in the air. Small size did not create flight. It made behaviors such as controlled descent, leaping, aerial correction, and eventually flapping more achievable. Balance changed as well. Most non-avian theropods carried long, muscular tails that helped stabilize the body and contributed to hindlimb mechanics. Early avialians retained long, bony tails, but later forms reduced the number and length of their tail vertebrae. New fossil evidence shows that vertebral reduction and tail shortening began before the final fusion associated with a pygostyle. Tail loss alone did not push the center of mass through one simple forward shift. The trunk, limbs, feathers, and mass distribution changed as interacting parts of the same body. Together, those changes created new balance conditions for movement on the ground and in the air. The body had become smaller and easier to control. It still needed a forelimb capable of folding, generating force, and surviving repeated wing beats. Bipedal dinosaurs had already freed their arms from walking. The forelimbs could specialize for grasping, brooding, display, balance, and other behaviors without preventing the animal from running. Across later theropod evolution, the wrist was reorganized. Small carpal bones changed position and identity. Near the origins of theropod flight, a bird-like pisiform replaced another wrist element called the ulnar. This was one late step in assembling the flight apparatus, not the single cause of flight. The new arrangement helped the hand fold alongside the forearm and later contributed to wing stability and control. The shoulder also gained a wider useful range of movement. Hand bones became reduced and increasingly integrated. These changes produced a forelimb that could fold compactly, carry an aerodynamic surface, and control force through a larger arc. The dinosaur arm was becoming a wing. A controlled wing still needed a chest and respiratory system capable of powering repeated movement. Changes in the chest followed a nonlinear path. Early paravians did not pass through one steady sequence of larger breastbones. Different branches carried different sternum shapes. In branches closer to modern birds, the sternum became larger, a complete keel developed, and expanded surfaces provided stronger attachment areas for flight muscles. The chest also carried structures with deeper dinosaur roots. A furcula, or wishbone, already existed in non-avian theropods. Its exact original function remains uncertain, but the bone was present before avian flight and later became integrated into the flying shoulder. Air sacs also extended through non-avian theropod bodies and entered parts of the skeleton. Fossils support a basic bird-like pulmonary design in some of these dinosaurs. They do not preserve every soft tissue connection needed to reconstruct the complete breathing cycle in every species. This respiratory inheritance did not create flight, but it became part of a body capable of sustaining intense activity while keeping the lungs ventilated. Watch one living bird wing beats. The hand folds during recovery, the wrist guides the outer wing, the shoulder redirects the whole limb, chest muscles pull against the sternum, feathers change angle to control force through the air. No part explains flight by itself. A working wing is an integrated system assembled from anatomy dinosaurs already possessed, and anatomy later branches continued to modify. Once that system became possible, evolution tested more than one aerial design. Microraptor carried long feathers on both its forelimbs and hindlimbs. Wind tunnel tests support stable gliding configurations, especially when control and trajectory mattered more than maximum efficiency. This four-winged body was not a required stage on the route to modern birds. It belonged to a specialized dromaeosaurid branch with its own aerodynamic solution. You followed an even stranger path. An elongated wrist element supported a membranous wing surface, unlike the feather-only wing of modern birds. Aerodynamic testing suggests that this system performed poorly compared with other flying and gliding vertebrate designs. It was a real aerial experiment, but not the design inherited by living birds. Other close avian relatives approached the physical thresholds proposed for powered flight. How many branches crossed those thresholds remains unresolved. The answer changes with the evolutionary tree, estimated body mass, reconstructed feathers, muscle assumptions, and the criteria used to define powered flight. The old debate between flight from the ground and flight from the trees also creates a false choice when treated too strictly. Different animals could climb, leap, descend, run up slopes, flap for stability, or combine several behaviors. Evolution was not refining one prototype. It was repeatedly discovering that feathers and forelimbs could interact with the air. Among these branches, one fossil preserves an especially revealing combination of active flight and unmistakable dinosaur anatomy. Archaeopteryx is often called a missing link. That label makes it sound like an incomplete animal trapped between two finished forms. Archaeopteryx was one functioning animal. Its jaws carried teeth. Its wings ended in 3 separate clawed fingers. A long chain of vertebrae formed its bony tail. At the same time, its wings carried asymmetrical flight feathers. The geometry of its wing bones is consistent with active flapping, probably during relatively short flights. Its stroke was not the same as that of a modern pigeon, and the fossils cannot tell us its exact launch behavior or endurance. It also lacked several shoulder and chest specializations that support the powerful flight stroke of many living birds. This mixture is the point. Bird-like wings did not wait for teeth, claws, and a long dinosaur tail to disappear. For millions of years, inherited dinosaur anatomy and new aerial adaptations operated inside the same bodies. Archaeopteryx was not halfway built. It was one successful arrangement within a much wider avian radiation. By about 130 million years ago, two major branches of early birds were already present. Early bird diversity was expanding. Some branches retained teeth, others reduced or lost them. Tail vertebrae shortened and fused in different patterns. Hands became more integrated, feet specialized for distinct habitats and behaviors. Confuciusornis represents one early toothless, short-tailed branch. It was not the universal ancestor of later birds. Enantiornithes formed a much larger radiation. They lived across the Cretaceous world and flourished for tens of millions of years. Their bodies combined effective flight structures with anatomical arrangements absent from living birds. Ornithuromorpha formed another major branch. It included the lineage leading toward crown birds. The features of modern birds were being assembled across this crowded radiation, not preserved inside one privileged chain of ancestors. No single feature marked a clean border between dinosaur and bird. Different combinations worked in different environments, and successful branches could still carry anatomical traits that later vanished completely. Forests, lakes, shorelines, and open ground contained competing forms with different diets, feet, wings, tails, and growth strategies. Then the entire system faced a global ecological collapse. 66 million years ago, an asteroid struck Earth. Dust, soot, and aerosols reduced sunlight, plant communities collapsed, food webs failed. Every non-avian dinosaur lineage disappeared. Most avian branches vanished as well. Enantiornithes left no living survivors. A small number of crown bird lineages crossed the boundary. Why those lineages survived remains uncertain. Global forest collapse offers one important clue. Birds tied closely to trees may have lost both habitat and food. Ground-associated lineages may have endured the early aftermath more successfully. Another hypothesis focuses on food. Seeds can remain available after above-ground vegetation collapses, so seed eating may have helped some early crown birds persist through the crisis. The fossil record does not reveal how much this mattered compared with habitat, location, and chance. No single trait explains the entire pattern. The impact acted as an ecological filter across bird diversity that already existed before the catastrophe. The survivors were not necessarily the strongest flyers or the most anatomically advanced. Their biology happened to fit conditions in a broken world. As ecosystems recovered, those surviving lineages expanded into newly vacant habitats. The dinosaur family had passed through its narrowest point. Return to the house sparrow on the branch. Its teeth are gone, its tail is short, its fingers are fused and hidden beneath feathers. Those changes did not erase its ancestry. They record it. The asteroid ended every non-avian dinosaur lineage. It did not end Dinosauria. A small surviving radiation crossed the extinction boundary and later expanded into eagles, penguins, hummingbirds, ostriches, crows, and pigeons. The bird outside the window did not replace the dinosaurs. It belongs to the dinosaur radiation that survived into the present. The dinosaur never vanished. It changed. It branched. And it survived.